Good day, students. Welcome to mathcodserve.com. In this clip, we're going to be going over how to find roots of polynomial functions by applying the fundamental theorem of algebra. The instructions for the problem that we are going to be solving are as follows. First, we are to find the number of complex, real, imaginary, positive, and negative roots of the polynomial equation. In number 2, we are to use the rational roots theorem to list the possible zeros of the polynomial. And then we'll proceed to use synthetic division and any factoring technique to express the polynomial function as a product of linear factors. And then we'll conclude by finding all the zeros and confirm the signs using Descartes' prediction in part 1, where we have to state the number of positive and negative roots. Okay? Now, let's take a look at the equation. What if we have the polynomial equation 6x to the 4th minus 29x to the 3rd plus 18x squared plus 9x minus 4 equals 0. Okay, let's start with the first part. We're to find the number of complex roots. So part 1, number possible. Let's just indicate number of complex roots. Number of complex roots. Now the number of complex roots using the fundamental theorem of algebra is basically the degree of the polynomial. Okay, so what is the degree of the polynomial here? The degree of the polynomial is the highest exponent for all the variable terms. So if you look at the exponents, we have 4, 3, 2, 1, and 0. The highest degree exponent is 4, so the number of complex roots, basically the degree, in this case, is equal to 4. Okay? Now let's take a look at the next part, the possible number of real roots. Okay, we know for a certainty that there will be 4 complex roots, and there could be a combination of real and imaginary roots. So let's look at the possible number of real roots out of the complex roots. Okay, so possible number of real roots. This is basically the degree or even numbers less than the degree. Okay, so you just subtract 2, 4, 6, 8 from the degree until you end up with 0 or greater. So the degree or even numbers less than the degree. Okay, so in this part we know that the degree is what? The degree from the previous part is 4. So the possible number of real roots is either 4. Now what's the first even number? 2, right? So if we subtract 2 from 4, we end up with 2. Okay, what's the next even number? Is 4. So we'll subtract 4 from 4, we end up with 0. So by looking at the degree or even numbers less, we're simply subtracting 2 from subsequent possible real roots. Okay, so we have either 4 real roots, 2 real roots, or 0 real roots. Now let's take a look at the possible number of imaginary. Okay, so the roots for the polynomial equation could either be real, imaginary, or imaginary. When we combine them together, we get the number of complex roots. Okay, so possible number of imaginary roots can be done by carrying out a simple arithmetic calculation. So all we simply do is look at the complex roots minus the real. Okay, the complex roots that are not real are imaginary. Okay, so let's carry out our calculations. We have a total number of 4 complex roots. Okay, now what if 4 of them are real? If there are 4 complex roots and 4 of them are real, then how many imaginary roots do we have? Absolutely none, because 4 minus 4 is 0. Okay, now what if out of the 4 complex roots that you have, 2 of them are even? I'm sorry, 2 of them are real. If 2 of them are real, then you're going to have the other 2 will be imaginary, because 4 minus 2 is 2. Now what if you have 4 complex roots and none of the complex roots are real? What does that mean? All 4 of them are imaginary. Alright, so you see the pattern here. You have 4, 2, 0, and you can just reverse it in the case of a situation where you have an even degree. Okay, so by carrying out this subtraction, you can easily see that the number of imaginary roots are 0, 2, and 4. Okay, so remember the equation complex minus real is imaginary, or imaginary plus real gives you complex. Okay, now let's shift gears and take a look at the next part. Now we're to find the possible number of positive roots. Okay, so possible number of positive roots. Okay, so in this case, what we're looking at is the number of sign changes of the function. Okay, let me just add an additional detail here so we avoid confusion. We're looking for the possible number of positive real roots. Okay, now when I talk about sign change for f of x, we are looking at a rule known as the Descartes rule of signs. That's what we're looking at here. So Descartes rule of sign basically involves looking at the sign change of the function and even numbers less than that. So the number of sign changes we have of the original function and even numbers less tells us the possible number of positive real roots that the related polynomial equation has. Okay, so we're going to write down the equation as a function form. Basically, f of x equals 6x to the 4th minus 29x to the 3rd plus 18x squared plus 9x minus 4. Now we have 1, 2, 3, 4, 5 terms. Now let's determine the signs of each term. The first term is positive. The second term is negative. The third term, positive. Fourth term, still positive. And the last term is negative. So the question here is, how many sign changes do we have in this polynomial function? So let's take a look at it. The first one, from positive to negative, that counts as a sign change. Sign change number 1. From negative to positive, that's another sign change. Number 2. Positive to positive, no sign change, that doesn't count. Positive to negative sign change number 3. Okay, so what does that tell us? It tells us that the possible number of positive real roots are either the number of sign change, which is 3, or an even number less than that. So if you subtract 2 from 3, you end up with 1. We can't go any further, because if we do, we end up with negative numbers, okay, which doesn't make sense. So it's either 3 positive real roots or 1 positive real roots. That's the result using Descartes' rule of signs. Okay, next we're going to find the possible number of negative real roots. Okay, so let's go ahead and do that. Possible number of negative real roots. Now this is similar to the strategy for finding the possible number of positive real roots. We're going to still use Descartes' rule of sign, but in this case we're going to be looking at the sign change of f of negative x. Okay, so let's write it down. We're looking at the sign change of f of negative x. Okay, number of sign change of f of negative x and even numbers less. Okay, so let's see what we have here. We want to determine what f of negative x is. We know that f of x is 6x to the fourth minus 29x to the third plus 18x squared plus 9x minus 4. So f of negative x is what? F of negative x simply means you evaluate the original function at negative x. So we're going to replace all the x's in this function with negative x. So you have 6 times negative x raised to the fourth power minus 29 times negative x raised to the third power plus 18 times negative x raised to the second power plus 9 times negative x minus 4. Okay? Now let's simplify this. F of negative x is going to be, now easy way to do this is remember that when you raise a negative term to an even power, the minuses group together in pairs, and minus times minus is plus, so the end result is a positive sign. Okay, so 6 times negative x to the fourth is an even power. We have two pairs of negatives, they pair up and they cancel each other out, so we have 6x to the fourth power. And then we have this right here. If you raise a negative number to an odd power, you still end up with a negative sign. Alright, so if we multiply that negative with this negative right here, we have positive 29x to the third. And then negative x raised to an even power becomes positive. Positive times positive is positive 18x squared. This is being raised to 1, which is an odd power. So the negativity still remains. We multiply that by plus. We have minus x minus 4. Okay, so what are we looking at here? Using Descartes' rule of signs, we're just examining the number of sign change and even numbers less than that. Okay, so let's see what we have here. The first term is positive, second term is positive, the third term is positive, the fourth term is negative, and the last term is negative. So how many sign change do we have in this polynomial function f of negative x? So positive to positive, no sign change, that doesn't count. Positive to positive, no sign change, that does not count. Positive to negative, that's a sign change, that's the first one. Negative to negative, no sign change, that doesn't count. So according to Descartes' rule of signs, the possible number of negative real roots is exactly 1. Okay? An even number less than 1 takes us to negative numbers, which is not applicable here. Okay, what we're looking for next is the possible rational roots. Okay, so your possible rational roots can be determined using the rational roots theorem. Okay, so possible rational roots. So your possible rational roots is the positive and negative factors of p divided by the positive and negative factors of q. Okay, positive and negative factors of q. So this tells us the possible rational roots. Okay, so let's go ahead and rewrite the polynomial function again. Let's see if we can write it. So, okay, there goes the polynomial function. So the polynomial function is f of x equals 6x to the fourth minus 29x to the third plus 18x squared plus 9x minus 4. Okay, so what is p and what is q? P is always the constant, and q is the leading coefficient. Okay, so you always have to make sure that you have a constant term there. If you do not have a constant term, then you have to carry out the necessary factorization of a GCF, so you have a constant term. All right, so let's see. What is P? P is the constant term right here. It's kind of backwards. You know the alphabet P comes before Q, right? But you kind of reverse it. When you're looking for P, you go from the back, and then Q is the leading coefficient. Okay, so P is equal to -4. It's always a constant, and Q is always your leading coefficient, basically the coefficient of the leading term. All right, so the positive and negative factors of -4 will be divided by the positive and negative factors of 6. Okay, positive and negative factors of 6. Okay, so what are your factors of -4? The positive and negative factors of -4. 1 goes plus or minus 1. 2 definitely goes plus or minus 2. And then 4 goes plus or minus 4. Now, what are the positive and negative factors of 6? Plus or minus 1 goes basically into every number. What else do we have? Plus or minus 2 goes into 6. 3 definitely goes into 6. And then 6 goes into itself. Okay? So now let's go ahead and generate the possible rational roots. So let's do that. So your possible rational roots, to determine this, what you do is you take one factor from the numerator and you divide it by every factor in the denominator. Okay? And then when you're done with that, you move to the next factor in the numerator and you divide it by every factor in the denominator. And then you do that until you exhaust all the numerator factors, and that will give you the possible rational roots. Let's do it. So if we are focusing on the first factor in the numerator, plus or minus 1, if we divide that by plus or minus 1, 1 over 1 is 1, so plus or minus 1. 1 over 2 is 1/2, so plus or minus 1/2. 1 over 3 is a third, so we have plus or minus 1/3. 1 over 6 is 1/6, so we have plus or minus 1/6. 2 over 1 is 2, so now moving to the second factor in the numerator, okay? The second factor of p, to be specific. So 2 divided by 1 is 2 plus or minus 2. 2 divided by 2 is 1 plus or minus 1. But we already have plus or minus 1, so we don't have to put it again. 2 divided by 3 is 2/3, so we have plus or minus 2/3. 2 divided by 6 is 2/6, which reduces to 1/3. We already have plus or minus 1/3. We don't have to do it again. 4/1 is 4, so we have plus or minus 4. 4/2 is 2, so we have plus or minus 2. Plus or minus 2 is already present, so we do not have to write it again. 4/3 is 4/3, plus or minus 4/3. And then 4/6 is 4/6, which reduces to 2/3, and we already have 2/3 accounted for. We do not have to write it again. Okay, so these are your possible rational roots. Now let's proceed to the factorization of the polynomial. To carry out the factorization of the polynomial, we're going to be using the factor theorem or remainder theorem to determine that. Okay, so let's proceed to the factorization. Now, if we divide the original polynomial function by any of these factors and we have no remainder, then that factor is a root. Okay. So in this problem, I'm going to be using the remainder theorem here. I'm going to be basically dividing using synthetic division. The reason why I'll be using synthetic division as opposed to the factor theorem is because the problem asks for the complete factorization of the polynomial. Okay, so let's go ahead and get started. We have 1, 2, 3, 4, 5, 6, 7, 8 positive and then 8 negative. So we have a total of 16 possible rational roots. So what does that mean? Well, we have to keep on testing and reducing our polynomial function until we end up with the complete factorization. Okay, so let's go ahead and pick a number and test it to see if it's a factor of the polynomial equation, and then we will continue from there. So let's start with positive 2. Why did I pick positive 2? Well, it's just a random selection. I just picked it randomly. Okay, so let's test x equals 2. If we divide synthetically with this root and get 0, then that is one of the roots. Okay, but if we do not get 0, then we have to move on to the next option. So we're going to make our synthetic division bar, and now we're going to extract the coefficients of our original polynomial function. So we have 6, negative 29, 18, 9, negative 4. Okay, so we're going to put the root here, 2. This is a possible rational root. And then we're going to proceed with our synthetic division. There is no number here, so we put a 0. What we're going to do is we're going to add down and multiply across over and over again until we end up with the last term. Okay, so we're going to add down and multiply across. Let's do it. 6 plus 0 is 6. Add down, multiply 2 by 6 and place it here, which is 12. Add down, subtract 9, 7, negative 17. Multiply across, you have negative 34. Add down, so we have 14 minus 8, 6, 2, 1, negative 16. Multiply across, negative 32. Add down, so we have 3, 23, negative 23. Multiply across, we have negative 64. Add down, negative 68. Okay? Now, what does this tell us? This is not 0. So, since this is not 0, x 2 is not a root, or x minus 2 is not a factor. Okay? So, since the remainder is not equal to 0, x equals 2 is not a root. Or you can say x minus 2 is not a factor. They mean the same thing, okay? So how do we proceed? We pick another candidate from our possible rational roots. Remember, these are possible rational roots. They are not the rational roots. So we're going to keep trying them out and see which one works. Okay, how about we test 4? Okay, so let's test x equals 4. See if that works. It's easier to try out the integers first because when you're dealing with fractions, it's a little bit more complicated. So let's put 4. We're going back to the original polynomial function. We extract all the coefficients. And then we divide using synthetic division. 0 here. You know what the drill is. You add down and multiply across. Okay, let's do it. 6 plus 0, 6, multiply across, 24. Add down, negative 5, multiply across, negative 20. Add down, negative 2, multiply across, negative 8. Add down, 1, multiply across 4. Add down, 0. Oh, perfect. This one gives me exactly what I want. Remember, we're looking for the roots that generate a remainder of 0. Okay, so since r is equal to 0, x equals 4 is a root, and x minus 2 is a factor. Okay, since the remainder is equal to 0, x equals 2 is, oh, sorry, x equals 4. I don't know where 2 came from. So x equals 4 is a root, one of the rational roots, and x minus 4 is a factor. Okay, so now let's write down the partial factorization of the polynomial function. It is now going to be x minus 4, the related factor of the root x equals 4, and then we are going to write down the depressed polynomial, okay, also known as your quotient. So it's going to be 6x to the third minus 5x squared minus 2x plus 1. Okay, how did that happen? Remember that your original function had a degree of 4. So when you factor out 1 degree, guess what? The degree of your quotient decreases by 1. Let me show you something. X to the 4 over x is what? X to the third, right? So that's basically what happens when you divide out a degree from a degree of another polynomial. You just subtract the exponents to get the degree of the depressed polynomial or the quotient polynomial. Okay, so this is a partial factorization. Now, let's continue. This polynomial function here, 6x to the third minus 5x squared minus 2x plus 1, I can't see any factorization tricks we can use here, so we have to go back to the possible rational roots. We already tested out 4, which was good, so we want to try another candidate with synthetic division and hope we get 0 as the remainder. So how about we test x equals 1? Is that a random selection? Well, you can select it randomly. I'm cheating here because I already know that 1 works. So yeah, let's go ahead and divide the cubic, the 4-term polynomial cubic, with 1. See what happens. Okay, so we have 6 -5, -2, and 1. We're testing 1. Let's see what happens. Add down, multiply across to divide using synthetic division. So you add down 6, multiply across 6, add down 1, multiply across. 1 times 1 is 1, add down, -1, multiply across, -1. Add down, remainder is 0. Perfect. Okay? So that's what I want. What does this mean? Since I have a remainder of 0. Since the remainder is equal to 0, that tells me that x equals 1 as a root, and the related factor x minus 1 is a factor. Okay? Now let's go ahead and write down the partial factorization. We had x minus 4 before. We have a new factor, x minus 1. And our depressed polynomial is going to be 1 less than this depressed polynomial here. So it's going to be 6x squared plus x minus 1. Set that equal to 0. Now, since we need the complete factorization, this remaining polynomial here needs to be checked for factorability. Okay? So can we factor this remaining polynomial here? This is a quadratic trinomial. We can proceed to use the remainder theorem and synthetic division to check to find more factors, or we can use another method that is less involved. So do you want to use synthetic division here? Is it wise, or is it smart, or is it effective to use synthetic division here? The answer is no, because we already know how to factor quadratics from algebra 1, algebra 2. So let's go ahead and just use our factorization techniques that we learned in previous courses to attack this quadratic trinomial here. I'm going to be using the x game to factor this out. So let's go ahead and do that. So using the x game, AC goes on top, B goes on the bottom. There are different ways that individuals factor quadratic trinomials. You could use the asterisk method, the box method, guess and check, whatever works for you. But I like the x game because it's very concise. Okay, so AC is -6 and B is 1. Now we play the game. What two numbers multiply to give you -6 and add to give you +1? The possible numbers that multiply to give you 6 are 1 times 6 and 2 times 3. Let's try 2 and 3. Because 1 and 6 gives me 5 or 7, that's no good. Let's fix the signs here. What if we have -2 and +3? If you multiply -2 and +3, you end up with -6. And then -2 plus 3 is +1. Perfect. So let's go ahead and factor this one right here. So remember, the goal is to factor 6x squared plus x minus 1. Factor that expression. Now, in this expression we have here, a is equal to 6. So that means we must factor by grouping. Okay, so we're going to have 6x squared, extract that -2x plus 3x minus 1. So we now have 4 terms, and we can factor by grouping, divvy down the center. From the first two, what's the GCF? The GCF from the first two is 2x. We extract that, and we're left with 3x minus 1. From the last two on the right side of the partition, the GCF is 1. You always keep the sign. We are factoring out +1, so there is no sign change occurring with these two terms to the right. So we have 3x minus 1. So whenever you factor quadratic trinomials by grouping, after this step, you always want to freeze and check to make sure that the quantities in the parentheses are identical. That means that your process is correct. If you have different terms here, that means you made a mistake and you have to go back to resolve the problem. These two quantities are identical, so that's perfect. factor them out, and then we are left with the outsiders, 2x and positive 1. Okay, these two will be grouped together in their own parentheses, and there goes the factored form of 6x squared plus x minus 1. Okay, so let's write down the factorization. We had x minus 4 and x minus 1 earlier using the remainder theorem and synthetic division. But now using the AC method, we're able to factor the quadratic trinomial, and we now have 3x minus 1 times 2x plus 1. We have a product of linear factors. Ladies and gentlemen, this is the complete factorization of the original polynomial expression. Okay, so let's just box our answer. To finish things off, we need to find out what the rational zeros are. What are the zeros? Okay, since we have the complete factorization, we will simply use the zero product property to wrap things up. Okay, so that involves setting every factor equal to 0, and then you solve the resulting algebraic equation with one variable on one side. So this one, you just add 4 to both sides. You have x equals 4. On this second one, you add 1 to both sides. You have x equals 1. This one right here, you add 1 to both sides. Let me show you the work. I know most of you can do this mentally, but I don't want to take any chances. So let me show you all the steps. So for the third one, we have x equals 1/3 as your third root. And then lastly, for this one right here, we subtract 1. We have 2x equals negative 1. And then we divide by 2 to get the last 0, which is x equals negative 1/2. Okay, so our roots, the roots of the equation, remember, are basically the zeros of the related polynomial function. They mean the same thing. Okay, so our roots are x equals 4. Let's do it in ascending order just to be organized. So x equals what's the smallest one? Negative 1/2, 1/3, 1, and 4. Okay, so these are our roots. Now earlier, remember we talked about Descartes' rule of signs. If you scroll back to the beginning of your notes, we said that let's take a look at it real quick. Okay, possible number of real roots, possible number of positive real roots. Using Descartes' rule of signs, we say they're either going to be 3 or 1 positive real root. Okay, so let's see what our answer is. So our answer has 1, 2, 3, 3 positive real roots, which is excellent, in complete agreement with Descartes' rule of signs prediction. And concerning the negative, the possible number of negative real roots, using Descartes' rule of sign, there was only one sign change. So we had only one possible negative real root, and what do we have? Exactly 1. So we have confirmation that Descartes' rule of sign is in fact correct. Thank you so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful in your study of polynomial functions of higher degrees, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions about anything in this presentation, just place your questions in the comment section below, and we will be more than glad to support you. Do subscribe to our channel for updates to other cool tutorials such as this. More clips can be found on math.serve.com. Thanks again for watching, and have a wonderful day. Goodbye.